Hi everybody. Who here is doing any kind of messaging in their solutions today? Few of you? Right. How many of you would describe yourselves as being event-driven anyway in that process? Okay. And who's doing microservices? The other buzzword du jour. That's it. Yeah, the rest of you doing monoliths, or the rest of you just aren't really sure what you've currently got? Okay. All right. So this talk is prompted a little bit by everyone's journey towards microservices and the slight problem that occurs when they begin to want to move away from a more direct RPC style interaction between their microservices and use events, because they rightly or wrongly have kind of learned that maybe about a better approach toward being more loosely coupled. And what happens to people when they try and do that in terms of the problems that they encounter, because there's some kind of secret sauce that isn't as well publicized as many of the patterns are in, say, when you're dealing with HTTP APIs. So this talk is really about trying to reveal those patterns to you. And I obviously can't hope to teach you all the detail. I'll teach you kind of why you might need them and what the bigger concepts are going on, and hopefully give you the right signposts for you to be able to go away and discover stuff, even if it's just giving you the right words to Google, because sometimes that's part of the problem. Okay, I'm iCooper on Twitter, if you want to follow me at any point. Okay. There's nothing really that exciting here. It just says I'm old. The bottom point basically is one I tend to raise. You know, I tell the story of how I got into speaking. It's when I started, I was a C++ programmer, and there's a new thing called .NET coming. And I was quite interested in it, and joined a few mailing lists, very smart people on the mailing lists from the Microsoft team, etc., talking about the thing they were building. And people in the US were going to user group meetings. Never heard of user group meetings before. Thought it was just a crazy idea. And they were always going to these .NET user group meetings in the US. So I posted on one of these mailing lists and says, "Well, when is everyone meeting in London? When is it? I don't know when that is." And someone said, "There isn't one, but if you started, I'll come." So I was never one to shy away from a challenge. So I started a user group. And the thing is, it's back in about 2002. At that point, there was no one to come and tell us anything. There's hardly anyone in Microsoft knew how to use .NET, let alone us get one of the rare people from Corp that had flown over through the country that actually knew something and come and talk to us. So we literally had to say, right, who's going to speak next week? And it would be someone's turn to get up in front of everybody else and explain something, go and investigate part of the .NET stack and do a little presentation on it. And that kind of forced me into regularly getting up and speaking. And that gets you through the sucky stage of I'm awful at speaking and it's scary. And eventually you become more comfortable with it, and you can kind of go around user groups around the country speaking to people, right? But a lot of it is about just doing it. Fear the fear and do it anyway, as they say. And it isn't about you being super smart or anything. It's just about you persevering long enough to actually do it. I'm no smarter than you guys. All right. I'm working on an open source project called Brighter. Anyone heard of it? So we kind of compete a bit with End Service Bus and Mass Transit on one side. We effectively are a framework doing messaging between parts of your stack in .NET or Python. And we also compete with Mediator. We don't say Mediator copied us because it came after us in terms of basically having a separation between command and handler. Well, lots of folks do command and handler. It's not like Mediator or we invented it. Okay. We're going to talk about this idea called data on the inside versus data on the outside. Has anyone read Pat Hellen's paper on this topic? Okay, so we'll cover that. You're all newbies on that one. And then we'll talk a little bit about various integration styles. So if I have some microservices, how do they talk to each other? That's what we refer to as integration. Okay. I'll talk about this war request versus events. Should my two microservices use a request-driven architecture or an event-driven architecture for integration? That will feed out the topic above. And then assuming we want to talk about events, we'll talk about a couple of key ideas that people don't always grasp. Pipelines and reference data, which are important to being able to actually then implement an event-driven architecture. And finally, we'll cover the slightly hoary topic of correctness, which is again something that burns a lot of people when they basically get into event-driven architectures. Okay. So this is a description of a service in SOA. I will go into the details in a second. And you might say, Ian, if you're giving a microservice talk, well, you're talking about SOA. That's that historical thing that that no one does anymore, right? So SOA and microservices are really the same thing. It's just that essentially microservices are effectively SOA 3. So what happened is that a guy called Don Box, who worked at Microsoft, found that talking between two COM objects when they were in different processes, called DCOM, was very hard. You had to open lots of ports, it was cryptic, people couldn't get it working, and thought there has to be a simpler way. So Dom effectively created a protocol called SOAP to do that. And basically he put the COM call that basically you were making, packaged it up inside HTTP, fired it over port 80. People said, my gosh, you can basically do RPC over HTTP. Wow, this is a whole idea. Let's call it web services. Basically created SOAP-based web services. And SOAP-based web services gave root to this idea of service-oriented architectures. Right. And Don Box described them having 4 tenets, and there are other things on the outside. So the first thing is our boundaries are explicit. Your service has a perimeter, which represents an explicit boundary, usually in the form of some kind of API. An API we generically mean not just an HTTP API, but it could be GRPC, it could be basically events. But you have some kind of contract where you say to consumers of your service, here is something that's going to be stable over the medium term. Right? You can write your code against this API, it'll be here next week. Inside your service is your implementation details of your service. I'm not making many guarantees about those to you because I want to have high product velocity. So I could be changing those 3 or 4 times a day because I've got continuous delivery. You can't rely on those. I want to be able to change them whenever I feel like it. I want to make my service go faster. I'm going to re-engineer the whole thing. It doesn't matter to you. You are depending on this stable boundary that I have offered you as my contract, my API. Provided I don't change that, you shouldn't care. Okay? And maybe what I also want you to do is be a tolerant reader. That's the way the internet works. So I want you to basically say, if I want 4 fields from your API and you give me those 4 fields, I don't care about the other 25 that you might put in there for other consumers, right? So you try and basically use a process which gives you effectively a reasonably stable external contract. And my service is autonomous. What does that mean? It means everything within this boundary I can release without dependencies on anything else in my platform or enterprise. Now, there's an important note. This is a logical definition and it's not a physical one. In SOA, the service might have multiple processes inside it, right? This notion some people have that a microservice or SOA service is a single process is wrong. One of the things, for example, here is that I have a database and I have basically a web server. I have 2 processes, okay? I can have many more. I may have a worker process, which is basically, I may separate my web component from my database essentially via a queue in order to decouple invocation, in other words, to throttle the rate to basically which stuff comes and hits my database. Another process, still part of my same service, okay? So there's nothing here about the number of processes inside, but everything in here has to be able to be released without dependency on anything outside, right? So I am autonomous. That means I own my own database, and it means I own my own data. Nobody else gets to peer inside the curtain and have a look at what my data is. My boundary is explicit. You can't take a dependency on the tables that I own. Right? So that basically means I am now autonomous. I am the single writer. I am the source of authority for that data. Nobody else gets to write it. Okay. Share schema, not type. In other words, please don't share .NET assemblies between services in terms of what your contract description is. Right, we use neutral formats like JSON, hopefully what we call a weak schema. Weak schema means essentially that we don't want you to enforce your type constraints too hard. If you're missing a field and you don't need it, who cares? Right? In fact, my policy is less used nowadays, but it said, hey, I want these 2 or 3 services to work together to do something, so they're going to have to make some agreements about some out-of-band activities. This is where you get all the WS specs that appear on WCF. Nowadays, the main things you would use with things like OAuth would be an agreement by policy that the way that you authenticate with my service is to pass me a bearer token. So what happened is we all went away and we built SOA, and that was SOA 1. Then we discovered that actually, we'll talk a little bit about that later, SOAP wasn't the greatest protocol in the world. And we came up with SOA 2 and SOA 2, so we should actually communicate via events. And you get what's called document literal as opposed to whatever the other one was, basically form of SOAP, right, RPC. And SOA was doing okay, and then essentially SOA 2, when it basically began to use events, ran into fell slightly afoul of basically vendors. Vendors wanted to get involved, and they created what is called the Enterprise Service Bus. The Enterprise Service Bus said, well, we will integrate all of your microservices for you, and they can talk to each other. And this one can talk HTTP, this one can receive events. It doesn't matter. Everything will go through this amorphous thing in the middle that will receive one and put out the other, and we'll put workflows in there. And it went horribly wrong. And the business logic began to migrate into this centralized service where all your workflow logic existed. Your services became dumb entity things that did CRUD, and all the logic existed somewhere in this thing in the middle that was probably called BizTalk. And that effectively nothing in there was testable, nothing in there was very maintainable. And it gave SOA quite a bad name. Okay. So there's a guy called Jim Weber. He's a Brit, and now works for Neo4j. And Jim came up with a thing called Guerrilla SOA, basically. Jim said, hang on a minute, let's just do, services are a really good idea. This notion of a service is a really good idea. We can just build those. Forget SOAP, let's just use HTTP, let's use REST or something simple like that, or maybe even use a lightweight broker like RabbitMQ, and we'll just build it like that. Forget all these big centralized architectures. Okay. Now, 2 forks of microservices happen from there, and lots of pain and confusion gets caused by which fork you're on, right? So Martin Fowler and James Lewis they work with Jim at ThoughtWorks, they take his ideas, long after Jim has left ThoughtWorks, and create microservices. And they're bringing some other concepts that have currency at the time, DevOps, DDD-style bounded contexts, Conway's law, or effectively inverse Conway maneuver, saying you should structure your organization around the architecture that you want to build, so you should structure your teams around microservices, right? That's microservices. But really, it's a load of policy about how to build microservices successfully. So it's not SOA, it just basically comes with a whole lot of best practices about building SOA in a way that works. The other route is a guy called Fred George. Anyone know who Fred George is? Heard of Fred George? Fred George worked at the Daily Mail for a while. That may some of you may enjoy that fact or not. But Fred basically came up with was the first person to really use the word microservices a lot. But he had quite a different model. So he basically worked at one point with Jim Weber. And he said, Jim taught me basically that 100,000 line monolith was bad, so I'm going to write 10,000 line microservices instead. And he said, you know what? My question to Jim was, what are the 100,000 line services? What are the 1,000 to 100 line services? And his model was essentially the human body. He said, effectively, in your body there are many cells. They cooperate basically to make you function. Each one of those cells has a limited lifespan. It gets replaced, it dies off, and basically replaced with new cells. He said services should be the same, right? You should write small services like 100 lines. You should keep them for about 6 months. And then you completely rewrite them by the end of that time period because you figure out how to do that better, or throw them away entirely because you don't need them. Don't have tests. You don't need tests for 100 lines of code. Write in whatever language you want, because if you don't understand the language, the last guy wrote it and you just rewrite it in something else. Right? Fred George is also responsible for a thing called program anarchy. Program anarchy, some people like. Program anarchy first thing we do is we fire all the product managers. Second thing we do is we fire all the QAs. The only people that matter are developers. Developers are like gods. And essentially all should bow before them. Fred's a good, it's an attractive proposition, but I think there's a bit of a touch of madness to what Fred wants.
Distributed monolith.
Well, yeah, exactly. That's very true. So I tend to stick much more towards the Fowler-Lewis model. I think it's slightly less, turn the amps up to 11. Okay. So I'm going to explain a little concept to you, and then we're going to forget about it. We're going to talk about other things, then we'll come back to it later. So one of the things about this model, obviously, is that although I say, well, all this data and my code is hidden away from you behind this boundary, obviously, it's not like a black hole, okay? My boundary is not an event horizon. Information must be able to leave my microservice. So if I make a call basically to my API, I may basically say, get me some data, and it will give me some data back. Or essentially, I may raise an event to say, something has happened. You may be interested by what happened to me inside. Now, the data that I'm putting on the wire doesn't necessarily have the same structure as the data inside my service, right? It probably reflects it, but essentially, while that contract is stable, I may be varying exactly how I've stored that to the database, etc., as much as I want inside. Don't expose your domain model directly here. Have some kind of anti-corruption layer. But an interesting thing about this data is that as soon as essentially it leaves my service boundary, it is stale. Right? It is now out of date. Because while you're done your get, someone else could come in and do a post and change the very piece of data you rely on. So the get information that you're now basically happily relying on is outdated because the post has already updated it. So the customer's phone number changed. You've got the customer's phone number via a get. Hey, I'm going to make the cut, go and call the customer. Meanwhile, someone else in another desk has posted customers changed their phone number. Right? Your data is stale. But we're aware of that. So we tend to basically, in things like HTTP, put information essentially like last modified date, it's actually saying if modified since, which is another thing. But the cache control header basically saying, how long will this data be valid for? How long can you keep it before? Essentially, you should check this data is still valid. A last modified or an E tag, which says, what version of the data do you have? Maybe when you work with the cache expires, you can ask me by sending if modified since and say, do I still have a current version of the data, or has someone else gone in and changed it in the background? Okay. And the same is also true of an event. When I publish an event, it is stale data now. Okay? But I can put version information in there. I can say this is version 314 or whatever, effectively, right? And you can say, okay, when I receive another event, it may say, and you want to use data later than 313 for the customer address because that's what I was associated with. Or you might want to say, actually, I used 314. Or you might want to say, hey, here's the new address. It's 312. Have you got anything later? I said, I've got 314. I can discard that data. I don't need it. Right. So this data is immutable, stale, and versioned. It's immutable because there's no point in my changing it. If I change it, nothing over here will get changed. The only way to change what's inside that database is to post something in through my boundary or put something in through my boundary. Okay. So Pat Helland, basically, he's an architect. He's been at Amazon, at Microsoft. He may be retired now, for all I know. Very, very, very smart guy. Wrote some very important papers. And one of them is called Data on the Inside versus Data on the Outside, where he identified this principle about reference data. Okay. And he said, essentially, you have inside data and you have outside data in the microservices world. Okay. And it's important to kind of understand that a bit later. But one of the things to really figure out about reference data is how highly cacheable it is. Okay. Because if you think about it, when I basically get hold of this information via GET, in a classic model of the web, be it basically an HTTP API or, for example, something on my website, there are a number of places I can cache it, right? I can cache it on a reverse proxy. So something like Nginx in front of my Kestrel-based web server effectively and say, hey, cache this data. You can hold on to it basically according to the cache control header, right, for a certain period of time. So that I don't actually have to do the walk of shame of calling again if the data hasn't changed. You know, and maybe it's got an E tag or an if modified, and all we'll do is just check with the origin server whether it's been modified, right? And I can get a 303 not modified back, and I can effectively set 3 or 4 other, and I can say essentially, hey, I can set it out of the cache. Or a forward proxy inside the enterprise that says, hey, I'm going to cache downstream of that upstream application. Even more likely, your application itself is in the browser going to have a cache of that data. And we do that to scale, right? The way the web scales basically is to cache data. And what it's caching is essentially reference data. It's stale, immutable, and version data that has left our microservice and traveled out into the outside world. All right. Let's talk about what I would tend to call the join problem. Okay. So once upon a time, we lived in the, some of us may still do, the happy world of microservices, right? Here you can imagine, so I use hotel booking for my examples. I know nothing about hotel bookings. I apologize to every single person in the room who's ever worked on hotel booking software. I only do it because if I end up using a domain I actually know something about, I get lost in the complexity. So picking a domain I know nothing about, I can simplify the whole thing in my own head. So imagine that I have a hotel kind of booking system, and I've got somewhere I can take direct bookings, and I can take those bookings for customers who already have an account with me, and I've got their credit card details stored. And when I take a booking, I want to inform housekeeping and the channel manager, which is telling sites like booking.com effectively how many rooms I have available, what price they are. Right? And let's imagine we've got a well-factored monolith. Right? This is not some big ball of mud. This is a pretty decently made monolith. We've got nice little modules that contain our various aggregates that we care about inside our monolith. And in this model, let's say I call an API to make a booking. Well, I probably go to the direct bookings module and I say, hey, I'm making a booking, and we run some code. And the booking says, let's store the booking first of all, maybe. Let's then go away and get some account information, perhaps, essentially for the credit card details that you're going to need to essentially be able to take the payment off the customer. And then when the customer pays successfully, I'll call housekeeping, and then we'll inform the channel manager that we've done the work. And it's all very straightforward because all of the data I need just lives there in the database, and I can get hold of whatever bit I need to fulfill my workflow. Imagine I've got microservices. Hopefully, I've got microservices for the right reason. That's when I want to scale my organization. And I need to have multiple teams who are capable of independently deploying against their own backlog. Okay. And let's say effectively I've now put it into a series of microservices. When my booking comes into direct bookings, don't know why it does that bit first. Yeah, it does that bit. And direct booking says, obviously I need to read the information from accounts to get hold of your credit card information, and then I will basically, after I've done that work, call housekeeping and channel manager. And then we go, but I can't do that because this violates all the rules we established earlier, right? This is essentially has to be a microservice. There must be an explicit boundary, and this is an implementation detail that you can't touch. If I rely on your schema of your database, I am in trouble because essentially now I've coupled these two and they can't actually be released independently because a change to the schema here will affect basically direct bookings. And this is often referred to as the join problem. What was easy inside my monolith, because I could reach into any table I felt like and create entities on demand and deal with them, suddenly becomes a problem because I now, from my direct booking service, have to figure out, well, how do I make a payment, right? I need to do that. I need basically information on the customer's credit card, and that lives in accounts. And I can figure out that maybe, I can call APIs and stuff, but this join problem is persistent for me, right? How do I fix it? Okay, so let's talk about what our different strategies can be for integrations between two processes. Okay. File transfer. So the oldest kind of trick in the book is file transfer, right? There's a location on file. Process A writes to it, process B reads from it. Okay. It has some really big advantages. One of them is that, generally speaking, it's a kind of lowest common denominator approach, and most libraries have some kind of support for I/O, even at a very basic level of, just the language libraries itself. And even if we're not doing I/O to the local disk, we're doing I/O to S3, for example, it's relatively accessible. Okay. And what this used to be effectively once upon a time was I'd have a mainframe, and my program would write basically to a tape, take the tape off, and I'd put it back as the input for the next process, and it would basically take that and then run the program and output another tape, etc. We keep doing that whole process, right? But it's actually quite effective, still effective today. The only problem becomes things like, well, okay, so effectively I'm writing to this location, how fast do I get notified that something new is in that location that needs reading? What is the format of that thing in that location? What happens if I want to essentially increase the throughput with which I read elements that have been written to that storage location by having multiple readers, but now I need to lock an item to say that process A is reading item 1 and nobody else should try and read it. But then say if process 1 fails, it should be returned to the pool and be read by somebody else. Or if I want to preserve ordering basically in those items, how do I do that? So you rapidly get into some complexity if you have a significant enough problem space here. But don't discard it altogether, right? It's very useful for very static data that is kind of hard to change. So I work nowadays at Just Eat, and we write menu data for a lot of our restaurants out to S3, and apps consume it directly from there because it is very slow changing data, and all we need to do is basically share it. Okay. So don't discard it, it's very effective. Okay. Shared database. Two processes communicate via effectively reading from the same database. Okay, so we've already said that there's a problem effectively here, which is the problem essentially that we want to be able to release our database independently, and I can't have two microservices depending on the same table because the schema dependency means they're now coupled. And essentially if I change the schema in one microservice, that impact of that rolls out to the other microservices. So I've now coupled my deployment of those two services, which violates the very point that I built them for in the first place, which is to have teams that are loosely coupled and able to work independently of each other, right? So in a microservices environment, between microservices, you never use shared database. You can, however, use shared database amongst the processes that live inside the microservice. So remember we talked about you might have a web process, a worker process, etc. In those contexts, it's okay to have a shared database. It's okay for those 3 or 4 processes to all use the same database because they are a unit of release and they'll all be released together. Okay. The other problem with classic shared database models, which is slightly less important but interesting, is the fact that the more things that depend essentially on your single data model, the harder it gets to actually provide a model that can meet everybody's requirements. So once upon a time, I worked for a company where my boss came to see me, and he said, and it's an insurance company, and he said, "I've been offered this model for £40,000, and this model, if you, I've been offered £40,000, guarantees to me basically all of a complete model for doing all insurance." He said, "This will save us enormous amounts of time on the new system we're building. We'll just basically use their model." And I said, "Can we get a view of this Uber model?" And I said, "Well," they're very reticent because obviously that's put in their secret source, but they've agreed that you can see the policy schema." So I saw the policy schema, and the thing is, they're right. They had modeled all insurance. So this policy object would do life insurance, ISAs, car insurance, households, everything. It had about 4,000 fields. And the point is, that's unusable, right, in terms of your application code. So your application code is going to take a fragment of that. You're now badly coupled to fields you don't understand. So actually, there's a whole simplification process, which is really where things like DDD come from, that work if you begin to basically say, my microservice has a smaller fraction of the model. Okay. From a procedure call, so two processes basically communicate by one process calling a method and another process, right? All the other techniques we'll see are data-based integration. In other words, I exchange a piece of data with you. This one is functional-based integration. It says I call a function that you own to get you to do something. Okay. As a result of that, we create what's called behavioral coupling. I am now dependent on the behavioral system and how it works. If you change that behavior, the ripple effect will basically impact me, even if the actual contract itself doesn't appear to have changed. And more importantly, there's a problem called temporal coupling, which we'll get to in a bit. In messaging, two processes communicate by sending a packet of data over a channel, right? Say synchronous. In other words, both processes don't have to be available at the same time. That's important. We'll come back to that again later. And it's a pipeline process, so you can transform messages in transit. Again, it's important. We'll come back to that later. And small messages, effectively sent frequently, can appear as though they're behavioral change. In other words, you can watch a stream of data, see changes, and look as though you're doing behavioral work. Okay. So, which do we tend to want to choose? So a lot of people nowadays, when they're building microservices, tend to default to an HTTP or a GRPC-based approach because it is simple. And the reason it is simple is because when I break up my monolith, I replace the calls that went between the various modules that were basically in-process function calls with out-of-process HTTP calls. And while that gets you started, it has a major problem. And the major problem is this. If effectively from my direct bookings I need to talk to the APIs of credit cards, accounts, housekeeping and channel manager, so I talk to basically the accounts API to get your credit card details, I pass that information to credit card payments, it makes a payment, and then I call housekeeping to update it, the room availability and channel manager to sell them on the outside, I have a problem if channel manager is not available. If channel manager is not available, my whole workflow in theory fails. Right. I now have what's called temporal coupling. All of my bits need to be available in order for the whole thing to work. So you can think about this like a phone call, right? Who makes phone calls still? Anyone? Right, yeah, my mum calls me. Yeah, make a phone call. And when I call on the phone, the problem is if you're not there, it's a very frustrating experience because I can't finish my communication. And essentially this is the model that you're looking at. Remember that effectively if I have 2, 3, 4, 5 services essentially, and each one of those services that I've got effectively has something like 99.9 uptime. My overall availability effectively is the product of those basically, so it's probably about 99.5, which may mean you're down for like 5 to 10 minutes a day. And that's okay, but imagine if you're just eaten, that's 10 minutes at 8 o'clock on a Saturday night. That's potentially millions of pounds of losses. Okay.
Specifically talking about HTTP requests for the architecture.
GRPC, we do.
So I could use a message bus for a request.
I'll come back to that later.
Which is almost like event-based.
Yeah, that's not a request-driven architecture. But we'll come back to that later. But yeah, so a GRPC or HTTP, but not specifically talking about HTTP, any RPC-based protocol. HTTP is not strictly an RPC-based protocol because it exchanges data rather than functionality, but it still has a temporal coupling problem. So when we think about a request-driven architecture. Okay. So the alternative is to use an event-driven architecture. With an event-driven architecture, what happens essentially is I have some kind of broker, and essentially I put a message onto basically the broker, and effectively I listen to it. And what happens is a logical channel, so I have some topic like effectively direct booking made, and then effectively interested parties basically subscribe to that message, right? So the consumer has the notion basically of the producer. So effectively I just put a message out saying, here's my, I've got direct booking, and housekeeping subscribes to that message, right? And it doesn't know who published it, and I don't know who consumes it, and we are therefore very, very coupled. There's no real coupling between our systems, and as such, that makes it very easy for us to deploy independently. But more importantly, for this model, we have something called guaranteed delivery. What that means is that because we have a queue attached to basically listening to the topic on the broker, the queue stores incoming messages. And as a result of that, effectively, even if I'm not available, the work will queue up and I can simply get to it when I am available. So in other words, this is Slack or WhatsApp, essentially, and it's the way that we have all moved away, effectively, from phone calls to a asynchronous process of communication because it's more efficient. You can get to that when you're ready, right? And that's exactly what this does. And overall, our availability is improved. Because now it doesn't really matter when I make the booking if channel manager is available. When it comes back up again, then it'll basically process the messages. And sure, there could be quite a long delay getting channel manager back up, but actually, traditional businesses' processes tend to be asynchronous. And they know how to solve these problems if they look back far enough. So for example, with a hotel, overbooking is a common problem, right? And usually there's somewhere basically solving the problem. So the other week I was basically in Manchester speaking at an event, and I booked in at the Holiday Inn Express, and they'd overbooked the Holiday Inn Express, but because I'm an HG member, they'd pushed me up to the Holiday Inn instead, right? So I got an upgrade, and I'm kind of like, well, this is great. So they deal with this kind of problem. I had a problem where for housekeeping, I arrived at a room with my not my current partner, but my ex-wife before that. And we went to basically a very fancy hotel in London for the night. And we arrived and they said, I'm very sorry, your room is not ready, right? This is a room that's costing about £500 a night. And we said, oh dear. They said, don't worry, go to the bar. Whatever you want is free. And actually, I don't know what the problem was. It took a couple of hours to resolve it. We didn't really care. After a couple of hours of drinking very expensive cocktails, who cares, right? So there are often traditional business process ways out of the asynchronous problem, effectively. If you can divorce that and just say, we'll eventually solve the problem. Okay. Right. So let's assume we are already at this point in our lives. We've got to the point where we understand that event-driven architecture is better, and we're trying to implement it. Okay. And we say, hey, my direct bookings come in. I'm going to take a payment because the customer has an account with us. And then we go, hang on a minute. I seem to still have the join problem. How do I get hold of the customer's credit card details? I could call the customer's, that should probably go to the API. I should call the customer API, but now I'm temporarily coupled. I can't talk to the database because that breaks the rules basically about isolation of my service. So where am I going to get the customer's credit card details from? Because I'm about to break my event-driven architecture, which I so lovingly created, because at this point I suddenly seem to need information that I don't have. All right, so what we're trying to do is explain to you how you solve that problem. All right. So there are two main solutions. In the left, basically we are going to talk about essentially pushing the information, well, pulling the information probably rather, and this one's going to be pushing it, right? So over here, essentially one option effectively is to say that when we receive a message in credit card payments, telling us to basically take a credit card payment, that message needs to include the relevant details that we need. In other words, basically what your credit card information is. So that's option one. We'll plan to do that in a second. And option two is I need a local store to my credit card payment service which tells me about that information. What are the card details? And those essentially are our two options. Let's explain those in a bit more detail. Okay. So in the first option, this is what happens. I recognize that messaging has essentially a pipeline. There's a data source, person publishing the message, and there's a data sink, the eventual consumer of that message. But I can have an arbitrary number of steps in between, and I can use that to enrich the content. So when the message comes in via direct bookings, I can say, hey, send that to the account. The account is what listens basically for direct booking made, and the account says, hey, does this customer have an account? In which case I'm going to add their credit card details to it, right? And then I publish a message, and that's what credit card payments listens to. And it says, okay, either probably the customer basically had no account and provided their credit card details at the time of the booking, or they were provided by the account. By the time I get to the credit card payments, I have added that information into the message. Right. So that's our first approach, is essentially to basically say we need to have effectively what we call a document message. In other words, a message that contains all of the content necessary for you to process the work.
Isn't your message get bigger at some point? Too big?
Messages can get big, yes. So we've got other solutions to talk about, right? But yeah. So this pattern is quite often thought of as choreography, right? In other words, essentially, there's no central controller of this process, but as events flow around the system, behaviors occur. Okay. It may be that we decide this flow of events around our system poses a problem to us, and that problem is that I don't really have great observability of it. If something goes wrong, I don't really understand how to basically insert that process and make something different happen. So I may choose to use an approach we call orchestration. Okay. And orchestration typically, effectively, is this idea essentially of a saga. Okay. So at some point, I've got a gateway, right? And a gateway just means something that lives over the top of my microservices and essentially coordinates them. And while there are technologies called gateways, like Amazon has a gateway, etc., forget that. It's a kind of misappropriation of the term, because They're using it because people want to, in that context, need that piece of infrastructure to help make that happen. But they're not really, that is not the gateway. The gateway is basically just a thing, a logical layer that exists above your microservices and coordinates stuff. Okay. And so what I can have here is something that says, okay, I will coordinate this process. I will send a message to direct bookings, or effectively, and say, hey, we've got a direct booking for you. And it will store basically, you know, a direct booking, and it may return a response to me with some additional information. And you can do request and response over a message, right? So I send you a message, and part of the message I include usually in the header is a reply channel. Reply back to me on this channel, right? It's usually just a queue, doesn't need to go through a broker. So they have a correlation, I did tie them up. So what happens in the gateway, typically with a Saga, is I have some kind of state machine and I save my work. I say, okay, booking number 123 has come in. So I will basically save my place, send some information to direct bookings, maybe it gives me some stuff back, and effectively then when its response comes in a bit later, I will listen to that message, get the correlation ID, wake up booking number 123 and say, okay, what's next? And it says to me, oh, you need to basically go and get some information about the credit card because it was a booking on account. Great. So what I'll do is I'll send a message to accounts and say, can you fill in the credit card details? Go back to sleep at the top, accounts base does the work effectively, etc. Adds in the credit card details, returns a response to me. I wake up because I received the message at the top and I say, hey, pick up the correlation ID. Now I have a message from a direct booking and I have some credit card information. What am I doing next in my workflow? Oh, I send it on to basically to the credit card payment system. Great. So I send the credit card payments and essentially it will give me a response at some point telling me the payment's been made, and then probably I update housekeeping and channel manager, etc. Right? And so the whole workflow lives in effectively what is a state machine up here. Okay, so you just have a state machine that you save to await a database, and every so often when events arrive, you wake it up and say, what does that trigger? Okay, it's a state transition, and that triggers some new step. That's all Sagas really are. You can implement Sagas from like stateless and maybe poly for reliability. You don't have to go and buy something expensive to do that. Okay. The advantage of Sagas is if things go wrong, you can get a response back which basically says we couldn't take the credit card payment. And you can then follow an alternative workflow which says, okay, I know how to deal with that. You can do that with orchestration, by the way. You can just raise a different event. But also the advantage here is to get a lot of observability. I can see what stage a given order is at. When someone phones up, you know, the customer helpline and says, I tried to book a hotel and effectively I've not had any response back, they can go, oh, well, we'll look in the database, we'll figure out what happened to your order. Right. Okay. The other option is to remember this. Remember we said that my service, as well as basically HTTP, might be raising events, and those events are effectively mutable style and version data, and they are easily cacheable. So in terms of basically when we think about the way that sometimes when we work, in my browser, when I'm using caching, rather than effectively calling the service to go and get the data, because I've got it before, I've got a local cache file and just read that local cache of the data. Right? And that can make my basic spar up or whatever quite efficient because it can just work a whole load on cache data and doesn't have to make that so many calls back to the origin server. So caching, if you think about it, is a way of me reducing the number of times I have to make requests to you for information. And in theory, if I pre-build that cache, you know, give you all the data effectively you'd normally go and request from me, well, then you haven't got to call me at all, right? And when a microservice that produces events about life cycles of entities effectively that exist within the microservice, downstream services can cache those events and build their own local copy of the data in the other microservice. It's read-only, right? I don't own that data, okay? It's immutable, I can't change it, but I can refer to it. So essentially what happens is I build a cache of your data that I might need. So rather than at runtime calling you to ask for that data, I already have a copy of it. Okay? And that's called basically event carriage state transfer. And Martin Fowler only named it for us a couple of years ago. We were all doing it beforehand. I used to call it reference data. Some people call it things like projections. Some people call it because that's a kind of term from CQRS, view models. You see various terms about it. But event carriage state transfer has got a reasonable amount of literature around it if you want to look at it. So the idea essentially is that as my account system gets a new account, or someone changes their credit card details, or someone changes their address, a worker in my credit card payments microservice updates a local reference data store, a cache of credit card details. And it may not retain all my details, it may retain just enough of my details that it needs to process credit card transactions. Okay. And that means when I get a request in saying, hey, Bristol credit card payments, can you please book this, or other event comes in saying, hey, credit card payment system, a booking's been made, can you take the payment? I don't have to call accounts, I have the data locally. And a really big advantage of this approach is that I now have a lot of isolation, in the sense that I don't care if the account service is currently working. It could be down for maintenance, but I can still process your booking, because I have a local copy of the historical data that you created. Okay. And that gives you this notion of bulkheads, this real useful property of fault tolerance and isolation, because my microservice has everything it needs to fulfill the inputs that come to it, right? It says, when I receive an event saying take a payment, I have all the information I need to do that. I don't need to talk to anybody else. I don't care about the status or uptime of any of the other parts of microservices in the infrastructure. I just care about what I can deliver. Okay. And that means in the event of failure, you quite often find that large parts of your system can continue to operate. And ECST is not really talked about enough, I don't think. And bizarrely, it's the worries about it is things like, I remember I was reading Ian Richardson and Jim Webber's book on REST in practice, and they refer to reference data, they refer to this idea, but they never explain it. They just they refer to it and assume that you knew what it was. And most people will skip over it because it's just a couple of sentences and they won't understand what that bit of the explanation was about how that worked. So it's good in a way that Martin Fowler's given it a name, because it means it's probably more likely people talk about it now. Okay. As a bank state transfer. That's a very common way of microservices avoiding runtime calls without the problem effectively of building up huge amounts of information inside a message as it's passed around the system in order to process everything. Okay. And in turn, at some point, my credit card payment system will raise its own events, which may also be cached downstream by other systems. Okay. The mechanism for reference data doesn't have to be using events, doesn't have to be ECST. Reference data is an idea, kind of predates CCST as a concept. So a really early idea people used to use an atom feed. If you go and look at Vaughan Vernon's book, I think on domain-driven design in kind of the .NET world, one of the things he talks about essentially is this idea of saying using an atom feed to expose events out of your microservice for other consumers. And it has a couple of nice properties. One is, of course, basically that with an atom feed, any page beyond the current page is immutable, which means it's highly cacheable, because you can look at the reference, the E tag, and say, have I read that page? So you only have to read back a limited number of pages before you know I've read that page, and then look and see what entries you already read on that page. And quite often you're just dealing with the current page in the stream. But the other advantage is you can read back from a new microservice to populate a new reference cache across a whole range, a whole history of data in the atom feed. Transform and load. So another common way people used to do this was actually replicate data between two data stores. You literally just use the fact that databases can replicate information because they ship logs. Those logs are effectively the events that happen in the database. And you can connect two of them up and just say, basically, you give me your event stream from your database and I'll copy it into this database and we'll use that locally. And if you go and look at most of the big investment banks in the City of London, they continue to use this process for doing basically building local stores for effectively microservices. They don't call it that because they don't tend to use that terminology, but that's effectively what they have been building in the past. The problem with using ETL as your mechanism for doing it is that it forces you usually to have the same database on both sides, right? And nowadays we're trying to avoid that. We want to have polyglot persistence. So essentially, if you need to get away from that, it has a huge advantage for you to actually decide that you're going to have, say, you know, a key value store on one side and a relational store on the other, because here I care about really rapid throughput for transactions, and here I'm actually doing some querying of the data. FTP. FTP is in theory workable, right? So FTP is essentially what we do when we say we're doing file transfer to basically communicate with some very long-lived static data between two processes, like basically, for example, a menu, right? If your data is slow-moving enough and there's not very much of it, and you haven't got a process at a high throughput, FTP is a reasonable option, right? So don't worry so much about how you basically transfer reference data, but today, the most common kind of model really out there is event carrier state transfer. Right? Types of reference data. I believe this slide is in the wrong order. Oh, it's in the right order. Okay. So Pat Helen classifies reference data, operand data. So that's the typical thing where essentially service A wants to talk to service B, and it needs some data to construct a message sensibly, like a product code or whatever, effective, etc. So you share that kind of information between services that just lets you have the vocabulary to communicate with another service. Shared collections. Shared collections are the most common use of this kind of replication. They're things like customer account data. So Just Eat, for example, has restaurant data in vast numbers of microservices, for example. Right? And historic artifacts. So historic artifacts are how we do reporting. So essentially, it says take a snapshot of the data in this service, put it into some kind of like OLAP store, effectively, and report on that. So this one, we take all of our data out of our individual microservices because we can't report across all those microservices with a join problem, and we collate it in some kind of big data store instead, and query over that as a process. Okay. All right. One thing to remember is that we are caching outside data, not inside data. Okay, what do I mean by that? So I mean that essentially you don't want to cache something that's effectively inside data from somebody else. If I was to call you and call you as an API, what would I get back? As opposed to what are the implementation details that produced that result? Okay. So a question that quite often comes up where I currently work is, if I was to call you and you were to tell me that the restaurant delivered to your area, that's a piece of cacheable data. If I was to call you and you were to give me all of the geospatial data, which was the restaurant's delivery area, that's an implementation detail. It tends to be not what I'll provide at the API. And the problem with giving you those internal details is twofold. One is I've now coupled you, because if I change my internal representation, what tends to happen is I now have to change the events that I'm raising, and that has a problem for downstream. We're trying to get away from that in the first place of a different contract. Second problem is I quite often couple behavior, because you have to know the rules, right? You have to understand how to interpret that geospatial data in order to make it work. So it means if we change it over here, I have to change it here. So you tend to want to focus on only the kind of data that genuinely leaves a boundary in response to a query. Think about what that would be. If I was to call you and ask you, this is a question, what would you give me? Okay, that's the data that ought to be on an event that I eventually then can cache downstream. Okay. So if you have to know the rules, it's not a good idea, right? So generally it's okay for me to have my own rules about your data. I've got some data from you. I can have loads of rules about what I do with your data, just as long as they're not a copy of your rules, because I'm trying to replicate what you do. Okay. Correctness. Okay. So if I am going to send an event downstream, I have a correctness problem. And ignore some of the things that I'll walk you through it, and then we'll look at the answer. So let's imagine I've got a service that takes orders, right? And I want to basically create an event to say that a new order has been created downstream. And what I intend to do is write basically down here to my table and say, I'm going to put in the orders table your new order, and I'm going to raise an event to my message broker telling downstream systems that basically there is a new order being created. I have a problem. The problem is this. If I basically write to the orders table, but failed to write to the broker, I now have orders up here that no one downstream has got. Unlikely my customer is going to receive their package until they phone up and complain and say, whatever happened to my order? Okay. So I could say, well, that's fine, I'm going to reverse that process. I will essentially send it to my message broker first and then write it to my orders table. Only if I succeed to go into my broker. That creates a reverse problem in the sense that my customer receives a package, but they have no record of the order in their order history. Okay. And the problem generally is that it's very difficult for me nowadays to do a transaction that encompasses those two pieces of technology. Usually they come from entirely different vendors and don't basically conform to a standard. The days when we could rely on everyone implementing MSDTC are long gone. And also distributed transactions don't scale very well. They're bottlenecks basically to scaling because they require agreement from everyone involved in the transaction. So what do we do? So the first pattern is called the Outbox Pattern. It's made famous a lot by the guys at Service and Udi Dahan. So that idea effectively says, in my database supports transactions, probably. We'll talk about what happens if it doesn't. And so I can have a transaction between the orders table and an outbox table. And in the outbox table, I write the message that I intend to send downstream, saying a new order was created. Okay. And then what happens is one of two things. So the process I prefer is this, right? I write basically to the orders table and I send the message over the message broker and someone downstream gets it. In the event that effectively, usually what happens is my broker says I've sent it, and what happens is I update the table and say, okay, I've sent that message. Okay. Now it's possible I'll fail to update the table to say I've sent the message. And in that case, effectively, what happens next will duplicate. That's fine. Downstream systems have to be prepared to receive duplicate messages. So what happens next is the little service that spins here reads the outbox table and looks for things that haven't been sent in a certain time window. Well, we haven't got a response back from the broker saying, I sent the message. We haven't filled in the outbox table. It says, I better resend that one then. I can't know whether it didn't send or that I didn't get the update, but what I'm relying on is that downstream you'll cope with that duplication. Okay, so that's why we call it guaranteed at least once delivery, not guaranteed once only delivery. Okay. So the idea is I say, okay, write to the orders table, run my message to the outbox table, send it on the broker, update the outbox table to show it was sent. In the event basically that I trawl this information and find it wasn't sent, and I resend it out over the broker, and I keep resending it until eventually I get notification saying it's done. Guaranteed at least once delivery, right? And downstream I had to have some mechanism to basically deal with duplicates. I'm either idempotent, in other words, applying the same message multiple times won't make any difference to me, or I have some kind of inbox that says, I'll take a record of messages I've received, and if I've already seen it, I will discard it. Okay. Log tailing. Let's go back one. There's a problem with this approach, though, that it tends to rely on the fact that I may be using an RDBMS, which allows me to have a transaction over multiple tables. If I'm using something like a document store, for example, like MongoDB, or even to some extent Dynamo, although it will work with Dynamo a little bit, I've got a problem that effectively I can't often have a transaction across multiple tables. So what do I do then? Right. So the second option is called log tailing. Generally, those databases that effectively don't support transactions do tend to support giving you all of the records written basically as a stream. So think of it a bit like having a trigger on the database and listening effectively to all of the things coming off that trigger continuously. And that enables me essentially, you could do it with triggers as well, I guess, to actually say, right, when I write something new to the orders table, what sends the message over the broker is something listening to the log, saying, hey, there was a new order added basically to the table, I will send a message to the broker. And this keeps retrying until it finally sends it. Okay. Log tailing. Third option is called state change capture. And the way state change capture works is it says basically, well, I'll write it to the broker, and then I will listen to messages on the broker myself to update my own table. So I've written to the broker has the message, and now I'll listen and update my own table. Only slight problem with this one can be that effectively the downstream system may be aware there's an order before the upstream system is. Someone's knocking on your door with your takeaway, and you're still wondering why your order hasn't basically marked as completed on your screen in front of you on the browser. But generally speaking, customers who receive their orders without basically having seen it complete are okay with that, right? But those are the three kind of approaches you need to care about. We're almost there. Last bit to tell you about. Logs versus queues. So one of the things that also comes up with this is whether effectively if you are sending a using event carrier state transfer to communicate between two microservices, you should effectively use a Keybase technology or a log-based technology. So a Keybase technology is something like RabbitMQ, SQS. Sends a notification. Notification effectively goes via a broker onto a queue. You listen to the queue, and when you've basically read the message, it is deleted. A log-based technology is something like Kafka or Kinesis, etc. Right? And what that says basically is I just move a pointer or even an atom feed up the stream. Right? So I never delete the message, I just increment where I am in terms of my reading position. Okay, why is that important? Well, if I have a shared queue, one of the problems that I get is that while it's fine working in a kind of normal context, what happens if I reach the point where effectively I introduce a new microservice and I want to initialize its cache with all of my reference data? I could simply go to my source, kind of like Outbox, etc., effectively, and say, well, I've got a whole load of messages in there, effectively, the things that I've sent previously. So I'll just resend all of those, right? And hope that the inbox down the far end can dedupe all the existing systems who've already seen those messages and can throw them away. But the problem with that is I flood my network with a whole lot of messages every time I want to introduce a new microservice and update its cache. And you get this problem a lot in QA and staging environments when I'm bringing, I suddenly spin up a new service into that environment, having destroyed my old one, and so I need to sync up with everything else that we've got, right? That's the problem with shared queues, is there's no way of effectively of easily creating a new cache. Also, I create a lot of data on the wire because every single basically consumer has its own queue with all the data. So the advantage of a log is that if I want to basically solve that same problem, I simply re-index the pointer and start again. Because I don't ever delete the messages, I just keep them for all eternity. And so that means essentially that while I started reading basically from 0 basically on the log and I'd got up to 15, somebody else can start reading at 0. And they can catch up with all the messages they've missed. And if you like the log, if you basically keep it permanently and you use something like Kafka's infinite storage model, which basically snapshots for you to make it a reasonable amount of data to store, allows you to essentially always spin up a new cache of the data that currently exists in an upstream data source. Right? And that's why today we tend to basically rely slightly more on, for this purpose, not for notifications, but for the purpose of basically event carried state transfer on log-based technologies like Kafka over basically notification-based technologies like SQS or RabbitMQ. All right. Okay. Cool. And we're done. There you go. Seems like an abrupt end, but I don't know quite how to wind you down after all that. But the point is, event-driven architectures are a very good way of providing isolation to your microservices, decoupling them basically from each other. But in order to achieve that, you have to understand how you do event-driven collaboration. And the way to do that is essentially to understand your problem you're going to face is always the join problem. And you've got to figure out which solution, and there may not be across the board, maybe in different scenarios you want to have different solutions, which solutions you need to basically deploy in order to effectively fix the issue of how do I get the data I need to service this request without making a request-driven call to another microservice. And the answer is either effectively you've got some choreography or orchestration that means that the message you receive has all the data you need to process it, or you've effectively had that data pushed to you earlier on by another process, so that essentially you have a cache of the other system's data so you can process quite independently of them. That's that. Thanks very much.